Assalamualaikum and good day everyone. In this presentation, we will discuss our mini project entitled Design and Implementation of a Variable AC to DC Power Supply 0 to 5 volt. This project was conducted for the Advanced Electronic course and focused on converting a high voltage AC input into a stable, adjustable low voltage DC output using fundamental power electronics principles. This project was carried out by 4 members, Aina Khalidah binti Muhammad Noor, Farah Nabila binti Maidin, Sabrina Fed Anak Dikol, and Siti Nurasha binti Kabrar. A DC power supply is an essential electronic system used to convert alternating current or AC into direct current or DC. Most electronic devices such as sensor, integrated circuits, and microcontroller require a stable DC voltage to operate correctly. In real-world application, the AC main supply is typically at high voltage level of around 220 volt, which is unsafe and unsuitable for low-power electronic circuit. Therefore, a power supply system is needed to reduce, convert, smooth, and regulate this voltage. This project demonstrates the complete AC to DC conversion process, including voltage, step-down, rectification, filtering, and regulation to produce a safe and adjustable DC output. The main objectives of this project are: first, to design a variable AC to DC power supply capable of converting a 220 volt AC input into a 0 to 5 volt DC output. Second, to apply theoretical knowledge of transformer, rectifier, filter, and voltage regulators in a practical circuit design. Third, to analyze and verify the circuit performance through calculation, simulation, and experimental testing. Finally, to gain hands-on experiment in power supply design and understand the importance of voltage regulation and thermal management. This slide presents the main components and tools used in this project. The primary component include a step-down transformer, which reduces the high AC input voltage, a bridge rectifier made of diodes to convert AC to DC, filter capacitor to reduce ripple voltage, and a LM317 adjustable voltage regulator to provide a stable and controllable DC output. In terms of software, NI Multisim was used for circuit simulation and waveform analysis. For hardware implementation, a breadboard, digital multimeter, oscilloscope, and connecting wire and laboratory power equipment were used to test and verify the circuit performance. This slide shows the complete circuit design of the variable AC to DC power supply. The circuit begins with a transformer, which steps down the 220 volt AC input to a low AC voltage suitable for electronic components. Next, the bridge rectifier converts the AC signal into a pulsating DC signal. A filter capacitor is then used to smooth the pulsating DC by reducing voltage ripples. Finally, the LM317 voltage regulator ensures that the output voltage remains stable and adjustable according to the required output level. This structure design ensures safe, efficient, and reliable DC power conversion. Before constructing the hardware circuit, the entire system was simulated using Multisim software. Simulation allows us to test the circuit under controlled conditions and observe the voltage behavior at different stages without the risk of damaging components. Through simulation, we can analyze the AC input waveform, rectifier output, filter signal, and regulated DC output. This step is important to ensure that the circuit operates correctly before proceeding to physical implementation. This slide shows the oscilloscope waveform obtained from the simulation, where channel A represents the AC input signal and channel B represents the DC output signal. The waveform displayed on channel A shows a sinusoidal shape, which is characteristic of an alternating current input supplied by the transformer. This confirms that the transformer is functioning correctly by providing an AC voltage waveform. On channel B, the waveform represents the DC output after rectification and filtering. Unlike the AC waveform, the DC signal does not alternate between positive and negative value. The comparison between channel A and channel B clearly demonstrates the successful conversions of AC voltage into DC voltage. This confirms that the rectifier and filter stage are operating as intended within the circuit. This result validates the effectiveness of the AC to DC conversion process in the design power supply. This slide shows the oscilloscope waveform at the output of the transformer stage. The waveform observed is a sinusoidal AC signal with a reduced amplitude compared to the input mains voltage. This indicates the transformer is successfully stepping down the voltage from 220 volts AC to approximately 12 volt AC. The shape of the waveform remains sinusoidal, which confirms that the transformer does not alter the frequency or waveform shape of the AC signal but only reduce its magnitude. This step-down process is essential for ensuring safety and preventing damage to downstream components in the circuit. This slide presents the waveform obtained after the rectification stage. The rectifier converts the AC waveform into pulsating DC waveform, which is clearly visible in the oscilloscope display. The waveform now contains only positive voltage cycles, indicating successful rectification. Although the voltage is now unidirectional, it still contains ripple and fluctuations. This is because rectification alone does not produce a smooth DC output. The presence of ripple voltage highlights the need for a filter stage, which is implemented in the next part of the circuit. This slide shows the waveform after the filter capacitor is applied. The ripple present in the rectifier waveform is significantly reduced. The voltage level becomes more stable and smoother compared to the rectifier output. This smoothing effect occurs because the capacitor charge during voltage peaks and discharge during voltage drop, effectively filling in the gaps in the waveform. The filtered DC voltage provides a suitable input for the voltage regulator stage, ensuring stable regulation performance. This slide shows the final output waveform after the voltage regulation stage using the LM317 adjustable regulator. The waveform observed is a stable DC voltage with minimal ripple, indicating that the regulator is functioning correctly. By adjusting the potentiometer, the output voltage can be varied smoothly within the desired range of 0 to 5 volt DC. This confirms that the power supply meets the design requirement of providing an adjustable and stable DC output suitable for electronic applications. In conclusion, a variable AC to DC power supply was successfully designed, simulated, and analyzed in this project. The circuit effectively converts a 220 volt AC input into a stable and adjustable DC output of up to 5 volt through the use of transformer, rectifier, filter, and voltage regulator. Simulation result and oscilloscope waveform confirm that each stage of the circuit operates as intended, demonstrating proper voltage step-down, rectification, filtering, and regulation. The use of the LM317 adjustable voltage regulator allows precise control of the output voltage, making the power supply suitable for various low-voltage electronic applications. Overall, the project objectives were successfully achieved, and the project demonstrates a clear understanding of power electronic concept and their practical implementation. That's all from us. Thank you.